There are 40 billion Earth-sized planets sitting in the habitable zones of their stars across the Milky Way galaxy. 40 billion worlds where liquid water could pool on the surface, where the chemistry of life could assemble itself, where something might be looking back at us the way we are looking at them. We have been listening for 65 years. We have processed 12 billion candidate signals. Every single one was noise. Zero. That number is not a failure. It is not a gap in the data waiting to be filled by a better telescope or a few more years of patience. It is a measurement, and the measurement is starting to alarm scientists in a way that the simple absence of signals never did before. Because the silence is not empty. It is full of information, and the information is getting worse. Consider what 40 billion worlds actually means. Picture yourself standing under a clear night sky, far from any city, where the stars press down on you like a ceiling of light. Every star you see is someone else's sun. Most of them have planets. Many of those planets sit at the right distance for water to exist as a liquid, for atmospheres to form, for the slow chemistry of life to begin its work. The galaxy should be humming. It should be noisy with the evidence of 10,000 civilizations rising and falling across deep time. Instead, when we point our most sensitive instruments at the sky and listen, what comes back is the sound of nothing, the hiss of empty space, the faint echo of the Big Bang cooling towards silence. And that silence presses back against us, the way the dark presses against a single candle in an enormous room. Every year, our instruments grow more powerful. Every year, we scan more stars at more frequencies with more sensitivity. Every year, the number at the end of every search pipeline stays exactly the same. The silence is not shrinking as our technology improves. It is deepening. That is not what you would expect if the galaxy were full of civilizations broadcasting into the dark. That is what you would expect if something were preventing them from broadcasting at all. This investigation will trace that zero through 76 years of science. From a lunch table at Los Alamos in the summer of 1950, where Enrico Fermi asked 4 words that still have no answer, to a paper published in Science Advances in 2025 that reframed the entire argument. We will walk through every major hypothesis that scientists have proposed to explain why the universe appears empty. We will examine the evidence that has accumulated across 7 decades of searching, and we will arrive at a conclusion that is not comfortable to sit with. If deep space keeps you up at night, hit like and subscribe before we begin. Now, take a breath. We begin. The first thing you need to understand is that the silence is not a puzzle waiting for a solution. It is a constraint. It tells us something about the universe that cannot be explained away by better equipment or more funding. The silence is the data, and the data is telling us that the path from a dead rock to a galaxy-spanning civilization is either extraordinarily improbable or extraordinarily brief. We do not yet know which, but we are starting to run out of room for optimism. Here is the scale of the problem. The Milky Way galaxy contains somewhere between 200 billion and 400 billion stars. It is roughly 6 billion years old. Earth formed about 5 billion years ago. That means the galaxy existed for roughly 9 billion years before our planet even existed. 9 billion years during which other worlds could have been forming, other biospheres emerging, other civilizations rising and falling and building things we might detect. If even a tiny fraction of those potential opportunities produce technological species, the galaxy should be visibly occupied. It should be loud. It is not loud. It is silent. And that silence has now been measured with enough precision that we can start to put numbers on what it means. Statistical models based on 6 decades of null results now constrain the number of detectable technological civilizations in the Milky Way to fewer than 1 to 5 per century. That is not a guess. That is what the data says when you run the numbers properly. A detectable civilization appearing once every 20 to 100 years across an entire galaxy of hundreds of billions of stars. That is not a crowded universe. That is a universe where something is systematically preventing civilizations from reaching the point where they can be heard. The question Fermi asked over lunch in 1950 was simple. Where is everybody? The question we are asking now is different. It is sharper. It is more personal. What is stopping them? To answer that, we have to go back to the beginning. We have to understand how we got to this point of certainty, and we have to trace the investigation through every dead end, every false alarm, every demolished telescope, and every hypothesis that seemed promising until the data caught up with it. The story begins with a quiet afternoon in New Mexico. Four physicists walking to lunch, a New Yorker cartoon about flying saucers, and a question that has festered for 3/4 of a century without resolution. Los Alamos National Laboratory, summer of 1950. The sun was high over the desert, baking the red dust and the low wooden buildings that still carried the smell of fresh pine from their construction only a few years earlier. This was a place built in wartime secrecy, carved out of nothing, where the most destructive force the world had ever known had been assembled by men in lab coats working through the night. The weight of that history pressed into everything. The fences, the guard towers, the quiet way people spoke in the corridors. Enrico Fermi, Edward Teller, Emil Konopinski, and Herbert York walked across the compound toward the cafeteria. The conversation was light. Someone mentioned a cartoon that had recently appeared in the New Yorker. It showed flying saucers piloted by little green men stealing trash cans from the streets of New York. The four men laughed about it as they pushed through the cafeteria doors and sat down at a table near the window. The room was warm. Trays clattered. Voices murmured in the close air. They discussed the recent wave of UFO reports in the news. They speculated about whether interstellar travel was even physically possible. They ate, and then, mid-meal, Fermi stopped. His fork hovered. He had been doing calculations in his head, the way he always did, the way he had done since he was a boy in Rome, running numbers behind his eyes while the world moved on around him. He was famous for this. During the Trinity test in 1945, standing miles from ground zero as the first mushroom cloud rose over the desert, he had estimated the yield of the atomic bomb by dropping pieces of torn paper into the shockwave and measuring how far the blast displaced them. His estimate, made on the spot with nothing but his own mind and falling scraps, was remarkably close to the instrument's measurements. He did not need a slide rule. He could feel the numbers the way other people felt the weather. At the lunch table, he had been running the numbers on a different problem: the age of the galaxy, the number of stars, the probability of planets, the likelihood of life, the time available for colonization. The numbers did not work. They were not close. They were not ambiguous. They were screaming at him. And what they were screaming was that the galaxy should be full. It should be impossible to look up at the night sky and not see evidence of 10,000 civilizations. But when you did look up, there was nothing. Nothing at all. He set down his fork. He looked at the other three men. The cafeteria noise continued around them, but something in Fermi's posture pulled the table into stillness. And then he asked 4 words. "Where is everybody?" The question hung in the air like smoke. Teller understood immediately what Fermi meant. His expression shifted. Konopinski and York understood a moment later. Fermi was not asking about flying saucers or little green men. He was not joking. He was asking about mathematics. He was asking why, if the galaxy was so old and so vast and so full of potential, there was no evidence of anyone else. He was asking how 4 men who had helped build the atomic bomb could sit in a cafeteria in the New Mexico desert and look at a universe that should have been crowded and find it completely, inexplicably, terrifyingly empty. No one answered. They finished their lunch in quiet. They pushed back their chairs and went back to work. But the question did not go away. It hung in the air over that table long after they had left. It spread through the scientific community like a slow infection. Michael Hart formalized the argument in a 1975 paper. Frank Tipler extended it in 1980. But the essential impossibility, the thing that Fermi named with 4 words over a cafeteria lunch, is the one that has never stopped being devastating. Here is the mathematics that Fermi was running in his head. The Milky Way is roughly 100,000 light-years across, a civilization capable of interstellar travel at even 1% of the speed of light could cross the entire galaxy in 10 million years. That sounds like a long time. It is not. The galaxy is 13.6 billion years old. 10 million years is less than 1/10 of 1% of the galaxy's lifespan. There has been enough time for this colonization process to happen thousands of times over. Thousands of waves of expansion, each one filling the galaxy with artifacts, signals, and engineering projects visible across interstellar distances. We should be digging up alien ruins in our own solar system. We should be detecting the infrared waste heat of megastructures around distant stars. We should be picking up stray communications from civilizations that have been broadcasting for millions of years. We should be living in a galaxy that is visibly, obviously, undeniably occupied. We are not. We find nothing, and that nothing is the most important piece of evidence in the entire field of astrobiology. In 1961, 11 years after Fermi's question, a young astronomer named Frank Drake sat down at the Green Bank Observatory in West Virginia to write an agenda for a meeting. The observatory sat in a quiet valley surrounded by the Allegheny Mountains, where the radio silence of the remote location was preserved by law. No TV or radio transmitters for miles, nothing that could interfere with the faint whispers coming from the sky. November had brought a chill to the air. The leaves had fallen. The building was quiet. Drake stood at a blackboard. A small group of scientists had gathered to discuss the search for extraterrestrial intelligence. He needed a framework to organize the conversation. He picked up a piece of chalk and began to write. What he produced became the Drake equation. It was not really an equation in the mathematical sense. It was a way of listing every factor that would determine how many detectable civilizations exist in the galaxy. A series of questions written in notation, each one a gate that life must pass through. You multiply the rate of star formation by the fraction of stars with planets, by the number of habitable planets per system, by the fraction where life emerges, by the fraction where intelligence develops, by the fraction that builds detectable technology, by the average lifespan of a communicating civilization. Multiply them all together, and you get N, the number of civilizations broadcasting signals we could detect right now. The chalk clicked against the board. The room was silent. None of the men in that room understood yet that this framework would outlive them, that it would become the organizing structure for one of the most consequential investigations humanity has ever undertaken. At the time, most of the variables were pure guesses. Drake set the fraction of stars with planets at 0, 2, 1 in 5. It felt generous. Many astronomers at the time thought planetary systems might be rare. They were wrong. The Kepler Space Telescope, which operated between 2009 and 2018, changed everything. Kepler stared at roughly 150,000 stars and watched for the tiny dips in brightness caused by planets crossing in front of them. It confirmed 2,783 exoplanets. Statistical analysis of that data showed that virtually every star in the Milky Way has at least one planet. The fraction went from 0, 2 to effectively 1. A five-fold increase. That should have been good news. More planets means more chances for life, more chances for civilizations, more chances for contact. Instead, it made the silence catastrophically worse. If planets are everywhere, the question is no longer whether there are enough places for life to begin. The question is why, with 40 billion Earth-sized worlds in habitable zones alone, nobody is answering. The equation did not solve the paradox. It sharpened it into a blade. Because the one variable that matters most, the one that could explain everything, is the one we cannot measure.
Oh.
The average lifespan of a technological civilization. If civilizations last for millions of years, the galaxy should be full. If they last for a few centuries, the galaxy would look exactly as it does.
Silent.
The equation organizes our ignorance. It does not cure it, but it forces us to confront something uncomfortable. Every measurable variable has moved in the optimistic direction since 1961. More stars, more planets, more habitable worlds. Life started faster than anyone expected. The silence has only deepened. That means the explanation must lie in the variables we cannot measure, and those variables point towards something disturbing. Consider the raw timescale problem from a different angle. A single civilization launching self-replicating probes at sublight speeds could fill the entire galaxy in a few million years. Frank Tipler made this argument in 1980 with devastating clarity.
You do not need faster-than-light travel.
You do not need generation ships. You just need one probe that can land on an asteroid, mine raw materials, and build copies of itself. Those copies launch to new star systems and repeat the process. The mathematics of exponential growth does the rest. One probe becomes two, two become four, four become eight. Within a few million years, the entire galaxy is saturated with probes. Every star system has been visited. Every asteroid belt has been mined. Every planet has been catalogued. The civilization that launched the original probe may be long dead. The probes do not care. They continue operating according to their original programming, maintaining the silence, watching, waiting. Patient in a way that nothing biological can be patient. Cold in a way that only a machine designed for deep time can be cold. They do not feel the loneliness of the void between stars. They do not measure time in heartbeats or generations or centuries. They measure it in the slow drift of orbits, in the gradual brightening of a star as it ages, in the quiet erosion of a mountain on an airless world over 1 billion years. They wait. That is what they do. They wait for the conditions that activated them to recur, or for new signals to reach their sensors, or simply for the universe to cool enough that their computation becomes more efficient. They do not grow bored. They do not degrade. They are not subject to the entropic decay that claims everything built by biology. They are built from metal and silicon and programmed logic, and they will outlast every living thing that ever breathed. We should be finding these probes in our own solar system. The asteroid belt between Mars and Jupiter is thick with raw material, rich in metals and minerals, the perfect supply depot for a self-replicating machine. If any probe had arrived here in the past 1 billion years, it would have found everything it needed. We should see evidence of ancient mining operations. We should find the hollowed-out cores of asteroids where the metal was extracted. We should detect the infrared glow of dormant machines still holding their charge, still listening, still waiting for a signal that never came. We should be tripping over alien artifacts on the moon. The surface has been undisturbed for billions of years. Anything that landed there would leave a mark that would not erode, would not weather away, would sit in the regolith unchanged until the sun itself expands and engulfs it. There is no wind on the moon, no water, no tectonic activity. An artifact placed there 1 billion years ago would look exactly as it did the day it arrived. We have mapped the moon. We have photographed its surface in detail. We have sent rovers and landers and sample return missions. We find nothing, not a single artifact, not a single probe, not a single piece of evidence that anyone has ever passed through this region of space. The asteroid belt is untouched. The moon is pristine. The Lagrange points where a machine might park itself to conserve energy are empty. We have looked, and the solar system is as still as it was the day it formed, as though no one has ever come this way. As though we are the first to arrive and find the lights off and the door unlocked and the silence pressing in from every direction. The absence of von Neumann probes in our solar system is one of the strongest pieces of evidence that something is systematically preventing civilizations from reaching the stage where they can build them. Because if even one civilization in the history of the Milky Way had built such probes, they would be here by now. The fact that they are not tells us that no civilization has ever survived long enough to build them, or that something destroyed them after they did. This is not a puzzle. This is evidence of a process we do not yet understand, and the evidence has been accumulating for 65 years, across dozens of search programs, using hundreds of instruments, processing billions of signals. Every single result points in the same direction. The silence is real. The silence is measured, and the silence is getting harder to explain with every passing year. The question Fermi asked that afternoon has a structure most people miss. It was not a mystery. It was a diagnostic. He had run the numbers and found a contradiction between what the math predicted and what the eyes saw. The contradiction demanded resolution. Either the math was wrong, or the universe was hiding something. Fermi died in 1954, 4 years after that lunch. He never published his calculation. He never wrote it down. The question passed into scientific folklore through the memories of the men who were at the table, but the mathematics behind it was reconstructed and formalized by others in the decades that followed. And every reconstruction confirmed what Fermi had seen in his head that afternoon. The galaxy should be full. It is not. Something is wrong. Here is the calculation, as it eventually took shape. The Milky Way contains roughly 300 billion stars on average across estimates, About 3/4 of those stars are red dwarfs, small and long-lived, burning steadily for trillions of years. The remaining quarter includes stars like our Sun, stable enough to support complex life over billions of years. Even if only 1 in a million of those sun-like stars produced a technological civilization at some point in the galaxy's history, that would be roughly 75,000 civilizations. And if even a fraction of those civilizations lasted long enough to develop interstellar travel, the galaxy would be colonized many times over. But Fermi was not thinking about fractions. He was thinking about time. The galaxy is old enough that a single civilization, expanding slowly, could have reached every star by now. The fact that we see no evidence of any such expansion means either that no civilization has ever attempted it, or that every civilization that attempted it failed. Both possibilities are disturbing. The first suggests we are alone. The second suggests we are next. When Frank Drake wrote his equation on a chalkboard at Green Bank in November 1961, he was not trying to produce a number. He was trying to organize a conversation. The meeting had been convened to discuss the search for extraterrestrial intelligence, and Drake needed a way to make sure everyone was talking about the same things. The equation was his agenda. The 7 variables he listed covered the entire chain from star formation to civilization lifespan. The rate of star formation in the galaxy, the fraction of stars with planets, the number of habitable planets per system, the fraction where life emerges, the fraction where intelligence develops, the fraction that builds detectable technology, and the average lifespan of a communicating civilization. At the meeting, the attendees plugged in their best guesses. Drake's own estimate produced roughly 10 detectable civilizations in the Milky Way. Carl Sagan thought the number might be in the millions. Others were more conservative. The equation did not resolve the disagreement, it exposed it, and in doing so, it accomplished exactly what Drake had intended. But the equation has a hidden property that makes it more dangerous than it appears. The first 3 variables are now known with reasonable precision. Star formation rates are well measured. The fraction of stars with planets is effectively 1. The number of habitable planets per system is roughly 1 in 5 for Sun-like stars. Multiply those 3 numbers together and you get a staggering number of potential homes for life. Tens of billions in our galaxy alone. The remaining 4 variables are where the uncertainty lives. And because they are all fractions multiplied together, any one of them being very small drives the entire product towards 0. The lifespan variable is particularly brutal. If civilizations last for 10,000 years on average, the galaxy could be full of them. If they last for 200 years, the galaxy would appear empty, even if millions had existed across cosmic time. The equation does not tell us which is true. It tells us that the silence can be explained by a single variable being small. The problem is that we are inside that variable right now, and we do not know how long our own civilization will last. Kepler launched in March 2009 with a simple mission: stare at a single patch of sky containing roughly 150,000 stars and watch for the telltale dimming that indicates a planet crossing in front of its host star. The mission lasted nearly a decade, far beyond its original design. By the time it was retired in 2018, it had transformed our understanding of the galaxy. Before Kepler, astronomers could only guess at how common planets were. The prevailing assumption was that planetary systems were relatively rare. Earth might be special simply because it had neighbors. Kepler destroyed that assumption. It showed that planets are not rare, they are ubiquitous. Virtually every star has at least one planet. Many have multiple. The fraction of stars with planets which Drake had set at 0, 2 in 1961, turned out to be close to 1. A 5-fold increase. The implications for the Fermi paradox are direct and brutal. If planets are everywhere, the silence becomes 5 times harder to explain. Before Kepler, you could argue that the galaxy might be empty because planets were rare. That argument is dead. The real estate is abundant. The problem lies elsewhere. Further analysis of Kepler data produced an even more startling number. Roughly 1 in 5 Sun-like stars hosts an Earth-sized planet in its habitable zone. Apply that to the Milky Way's 300 billion stars, and you get roughly 40 billion Earth-sized worlds where liquid water could exist on the surface. 40 billion potential cradles for life, and we have not detected a single signal from any of them. Each new exoplanet discovery tightens the paradox. Every announcement of another Earth-sized world in another habitable zone should be cause for celebration. Instead, it is another data point that makes the silence more inexplicable. The galaxy is not short on real estate. It is short on broadcasters. The oldest confirmed rocks on Earth are about 4 billion years old, but the evidence for life goes back even further. Isotopic signatures in ancient carbon deposits suggest that life was present 2 billion years ago. The planet itself formed 54 billion years ago. That leaves a window of roughly 300 to 400 million years between the formation of the planet and the appearance of life. That window is significant because much of it was hellish. The early Earth was molten. The surface temperature was high enough to vaporize water. Asteroids and comets bombarded the surface relentlessly during a period called the Late Heavy Bombardment, which peaked about 9 billion years ago. Conditions were, by any reasonable standard, terrible for the emergence of biology. And yet life appeared anyway. It did not wait for perfect conditions. It did not require a billion years of slow chemical experimentation. It started as soon as the planet cooled enough to sustain liquid water. That is a data point with enormous implications for the Fermi paradox. If abiogenesis is easy, if the transition from non-living chemistry to self-replicating biology happens readily under the right conditions, then life should be common across the galaxy. The 40 billion Earth-sized worlds in habitable zones become 40 billion potential biospheres. The silence then cannot be explained by life being rare. It must be explained by something that happens after life begins. The gap between the planet's formation and the appearance of life is only 300 to 400 million years. In geological terms, that is fast. Life did not struggle for billions of years to gain a foothold. It established itself almost immediately. If that pattern holds elsewhere, the galaxy should be teeming with biology. The fact that it is not means the filter is not at the origin of life. It is somewhere further up the chain. Now we arrive at the problem that makes everything else seem small. The problem of deep time. The Milky Way is 13.6 billion years old. Earth is 5 billion years old. That means the galaxy existed for more than 9 billion years before our planet even formed. 9 billion years during which countless stars were born and died, countless planets formed and cooled, countless opportunities for life to emerge and evolve into something that could cross the space between stars. Consider what a single civilization could achieve in that time. A spacecraft traveling at 1% of the speed of light could cross the Milky Way in about 10 million years. That is a long time by human standards. It is nothing on cosmic timescales. The galaxy has had 1,360 times that long to produce a civilization capable of building such a spacecraft. Frank Tipler's 1980 argument about self-replicating probes makes the scale problem even more stark. A single probe that can mine asteroids and build copies of itself could saturate the entire galaxy in a few million years. The copies do not need to be sophisticated. They just need to be functional, and they do not need to be fast. Even at sublight speeds, the exponential growth of the probe population ensures that every star system is reached within a geologically brief period. We should be finding evidence of these probes everywhere. They should be in our asteroid belt. They should be on the moon. They should have left traces in the geological record. We find nothing. Not a single artifact. Not a single piece of evidence that anyone has ever been here. The absence of any sign of galactic colonization is not a puzzle. It is a constraint. It tells us that either no civilization in the history of the Milky Way has ever attempted to build self-replicating probes, or that every civilization that attempted it was destroyed before the probes could complete their mission. Both possibilities point towards something that systematically prevents civilizations from reaching the stage where they can expand beyond their home star. This is not a mystery waiting to be solved by a better telescope. This is evidence of a process. And the process is operating on a scale and time span that dwarfs anything in human experience. The silence is not a gap in the data. It is the data, and the data is telling us something we do not want to hear. The galaxy formed roughly 13.6 billion years ago. The first stars ignited within a few hundred million years of that. The first planets formed around those stars. The first opportunities for life existed more than 13 billion years ago. Earth did not exist until 5 billion years ago. That means the universe had more than 9 billion years of head start on us. 9 billion years during which life could have emerged on countless worlds, evolved intelligence, built civilizations, and expanded across the galaxy. If even a single civilization had done this, we would know. The evidence would be everywhere. The deep time argument is the most difficult to counter. You can argue that life is rare. You can argue that intelligence is rare. You can argue that technological civilization is rare. But the timescales involved are so vast that even extraordinarily rare events become common given enough time. A 1 in a trillion event happening once per trillion years is irrelevant. A 1 in a trillion event happening once per year across a galaxy of 300 billion stars becomes likely within a few thousand years.
Multiply that by 13.
6 billion years, and the improbable becomes inevitable. And yet, the galaxy is silent. That means the probability of a technological civilization arising and surviving long enough to become detectable is not just small. It is effectively zero. The silence is not a statistical fluke. It is a statistical certainty that something is preventing civilizations from reaching the stars. The deep time argument forces a conclusion that most people find uncomfortable. If the galaxy has been silent for 6 billion years despite having every opportunity to produce civilizations, then the silence is not temporary. It is permanent. It is a feature of the universe, not a bug. And if it is a feature, then we are living inside a constraint that we do not yet understand. Robin Hanson, the economist who formalized the Great Filter concept, extended his argument in 2021 with a model he called grabby aliens. The idea is simple. If civilizations exist that expand aggressively at a significant fraction of the speed of light, they would produce visible expansion fronts. Those fronts would be detectable as boundaries between transformed and untransformed regions of space. We would see them in our telescopes as sharp edges in the distribution of matter and energy across the galaxy. We do not see such fronts. The galaxy looks natural. It looks untouched. There are no zones of engineered stars, no regions where the infrared signature suggests massive energy harvesting, no boundaries that indicate one civilization's territory ending and another's beginning. The galaxy looks exactly the way it would look if no technological civilization had ever built anything at scale. Hanson's model calculates what the galaxy should look like under different assumptions about the rarity and expansion speed of civilizations. The results are sobering. For the galaxy to look as empty as it does, detectable civilizations must be extraordinarily rare. His estimates suggest that grabby civilizations arise at roughly 1 per million galaxies. That is not a galaxy full of neighbors. That is a universe where civilizations are so rare that we might be the only one in our entire galactic neighborhood. The model also produces a timeline. If grabby civilizations exist elsewhere in the observable universe, their expansion fronts are spreading outward right now. They are converting matter and energy into engineered forms as they go. The nearest front should reach us somewhere between 200 million and 2 billion years from now. On human timescales, that is irrelevant. On cosmic timescales, it is soon. The grabby aliens model does not solve the Fermi paradox. It sharpens it. It tells us that the silence is not just a local phenomenon. It is a galaxy-wide constraint, and it gives us a framework for understanding what the silence actually means. The mathematics of the Fermi paradox is not complicated. It is not subtle. It is brutal in its simplicity. The galaxy is old. The galaxy is vast. The conditions for life appear to be common. The silence is absolute. Something has to give. The math demands that at least one of the following must be true. Life is extraordinarily rare. Intelligence is extraordinarily rare. Technological civilization is extraordinarily rare. Or technological civilization is extraordinarily short-lived. Those are the only possibilities. Everything else is speculation. The exoplanet revolution has effectively ruled out the first possibility. Life's building blocks are everywhere. The conditions for abiogenesis appear to be common. Life started quickly on Earth. The math says life should be common in the galaxy. The remaining possibilities all point in the same direction. Something is preventing life from reaching the stage where it becomes detectable across interstellar distances. That something could be biological, geological, sociological, or technological. But it exists. The silence proves it. The question is not whether the filter exists. The silence answers that. The question is where it sits. And that question is the most important one humanity has ever faced. Because if the filter is behind us, we are the lucky survivors. If it is ahead of us, we are the next in line. The mathematics does not tell us which is true, but it does tell us that we cannot afford to be wrong. The search did not begin with a grand strategy or $1 billion facility. It began with one man, one telescope, and a quiet April morning in West Virginia. Frank Drake was 29 years old in 1960. He had recently joined the National Radio Astronomy Observatory at Green Bank, a facility so new that the roads were still unpaved. The morning he began the project, the air carried the chill of an Appalachian spring. Frost still clung to the grass in the hollows where the sun had not yet reached. The mountains stood in close around the valley, their ridges dark against a pale sky, quiet in a way that felt old, the kind of quiet that settles into the bones of a place and never leaves. The telescope available to him was modest by any standard, an 85-foot dish of riveted steel, built for mapping the hydrogen line, not for hunting aliens. It rose from the valley floor like a question mark aimed at the void. The dish did not move the way later telescopes would move. It was fixed in place, relying on the Earth's rotation to sweep the sky across its focus. Drake had to convince his superiors that pointing it at nearby stars was a legitimate use of telescope time. They agreed, perhaps out of curiosity, perhaps out of respect for a young astronomer who had already shown he would go where the data led him. He chose two targets, Tau Ceti, 11, 9 light-years away, and Epsilon Eridani, 10, 5 light-years away. Both were sun-like stars, close enough that a signal of moderate power might be detectable. He tuned the receiver to 1,420 MHz, the emission frequency of neutral hydrogen. Giuseppe Cocconi and Philip Morrison had published a paper in Nature the previous year arguing that this was the logical channel for interstellar communication. Hydrogen is the most abundant element in the universe. Any technological civilization would know about the 21-centimeter line. It was the obvious place to listen. The one frequency that any two species, no matter how different, could agree on. Drake called the project Ozma, after the queen of the fictional land in L. Frank Baum's Oz books, a ruler of a place far away and difficult to reach. The name was apt. He listened for roughly 150 hours spread across 6 days. The receiver hissed with the background noise of the galaxy. He sat in the control room, watching the instruments, watching the paper printouts unspool with their columns of numbers, waiting. The mountains outside stayed silent. The dish stayed fixed on its target. The universe did what it had always done. It gave nothing away. At one point, a strong pulsing signal came through. The team froze. They checked the equipment. They checked the coordinates. They checked everything they could think of. The signal turned out to be a high-altitude aircraft passing through the telescope's beam. After that false alarm, the rest was silence. Project Ozma found nothing, but it established the pattern that every subsequent search would follow. Point the telescope. Listen. Find nothing. Repeat with a better telescope. The pattern has not changed in 65 years. On the night of August 15, 1977, the Big Ear radio telescope at Ohio State University was doing what it always did, scanning the sky automatically, recording signal intensities on continuous paper printouts, producing columns of alphanumeric characters that researchers would review by hand the following day. Jerry Eamon was a volunteer astronomer working through the data. He had done this hundreds of times before. Scan the columns. Look for anything unusual. Move on. But on this particular printout, one sequence stopped him cold. At exactly 1420, 726 MHz, the hydrogen line, a signal appeared that was roughly 30 times louder than the background noise of space. The peak intensity exceeded 250 Yunskis. It lasted exactly 72 seconds, the maximum time a celestial source would remain in Big Ear's beam as the Earth rotated. The signal behaved exactly the way an extraterrestrial transmission should behave. Eamon circled the character sequence 6EQJ5 on the printout. He wrote a single word in red ink in the margin.
Wow.
To understand what 250 Yanskis means, imagine the difference between a whisper and a shout in a completely silent room. The cosmic background at that frequency is the whisper.
The wow.
Signal was someone shouting directly into the microphone at exactly the frequency that Cocconi and Morrison had identified in 1959 as the universal communication channel. The signal never repeated. Eamon and others pointed Big Ear at the same patch of sky hundreds of times over the following years.
Nothing.
Other telescopes searched the same coordinates. Nothing. The signal came from the direction of the constellation Sagittarius, from a region with no remarkable star or object. For the next 40 years, the WOW signal sat as the single strongest candidate for an extraterrestrial transmission in the history of SETI. One burst,
72 seconds.
then silence. In 2017, an astronomer named Antonio Paris proposed an explanation that seemed to close the case. Two comets, designated 266P Christensen and P2008Y2, had been in the general area of Big Ear's beam on the night of the detection. Paris argued that hydrogen clouds surrounding these comets could produce emission at 1,420 MHz, mimicking the exact signal Eamon had detected. The explanation was comfortable. It gave the wow signal a natural origin. It allowed the broader scientific community to move on. Several media outlets reported the mystery as solved. The comet hypothesis entered popular science articles as the accepted explanation. Except there were problems from the start. Other astronomers pointed out that the comets in question were not actually in the correct beam position on that date. Big Ear had two feed horns, and the geometry did not place either comet in the right one. More fundamentally, comets emit radio signals at 1420 MHz at extremely low power. The kind of emission a hydrogen cloud around a small comet can produce is many orders of magnitude weaker than 250 Yanskis. It was like proposing that a candle caused a forest fire visible from orbit. The scale was wrong. The debunking of the comet hypothesis happened gradually. Multiple researchers published critiques between 2017 and 2018. But the debunking never got the same attention as the original claim. In popular culture, the comet explanation stuck. It was clean. It was simple. It let people stop wondering. Then, in 2025, a team decided to go back to the beginning, straight to the paper. The actual physical printouts from Big Ear's observation run in August of 1977. 75,000 pages of dot matrix output, sitting in archives for nearly half a century. Nobody had done a full systematic reanalysis of the original data in decades. The results destroyed the comet hypothesis and replaced it with something nobody expected. The 2025 reanalysis was painstaking. Researchers used optical character recognition to digitize over 75,000 pages of Big Ear's archival dot matrix printouts from the 1970s. These were the original data records, the raw output of the telescope's receiver system. Nobody had conducted a full systematic review of this volume of material since the signal was first detected. The results confirmed what Eamon had seen that night, but with greater precision.
The wow.
Signal's flux density exceeded 250 Yanskis. At that power level, the comet explanation collapses completely. Comets at 1420 MHz produce emission measured in millijanskis, thousands of times below the observed intensity. And the positional analysis confirmed what critics had argued for years. Neither comet was actually located in the correct feedhorn beam on that date. The geometry was wrong. The power was wrong. The comets could not have produced this signal. So if it was not a comet, and it was not terrestrial interference, and it was not a satellite, what was it? The new best hypothesis is stranger than any of those explanations, and stranger than aliens. Researchers now propose that the WOW signal was a rare superradiance event, also described as a hydrogen maser flare, possibly triggered by a magnetar. In plain terms, under specific and unusual conditions, a cloud of cold hydrogen gas can be stimulated to emit a sudden, intense burst of radiation at exactly 1420 MHz. If a magnetar, a neutron star with an extremely powerful magnetic field passes near or through such a cloud, it can trigger this kind of coherent emission. The result is a one-time cosmic belch of perfectly tuned radiation. Powerful, brief, non-repeating. This explanation fits every observed characteristic. The frequency is exactly right, because the emission comes from hydrogen itself. The intensity is consistent with superradiance amplification, which can produce enormous power from a relatively small cloud. The 72-second duration matches the beam transit time, meaning the source appeared to be at a fixed point in the sky. And the non-repeating nature makes sense, because superradiance events are rare and depend on a specific alignment of conditions that may never occur at the same location.
The wow.
Signal was not intelligence. It was not comets. It was something the universe produced naturally, but so rarely that nobody had predicted it. The cosmos generated a signal that perfectly mimicked what we expected from an alien civilization, at exactly the frequency we were listening on, and it did so through raw physics. This mattered beyond the wow signal itself. It established a pattern that would repeat throughout the history of SETI. Every time scientists believed they had found evidence of technology, the universe offered a natural explanation that no one had anticipated. Pulsars mimicked regular transmissions. Comets were blamed and then cleared. Superradiance produced a perfect fake. And the question got harder. If the universe keeps generating false positives that look exactly like intelligence, how would we recognize the real thing if it ever appeared?
The wow.
Signal was not the first time the universe had fooled us. It was not even the most dramatic. In 1967, a graduate student at Cambridge named Jocelyn Bell Burnell was analyzing data from a radio telescope designed to study quasars. She noticed a signal, a rapid, precise pulse repeating every 337 seconds. Nothing natural was known to pulse with that kind of regularity. The research team labeled the source LGM-1, Little Green Men. They were half joking, but only half. For weeks, the possibility of an artificial origin sat on the table. Belle Burnell and her supervisor Anthony Hewish considered it seriously. Then a second pulsing source was found in a different part of the sky, and then a third. The explanation turned out to be rotating neutron stars, collapsed stellar cores spinning at extraordinary speeds, sweeping beams of radio energy like a lighthouse. The signals were natural. They were called pulsars. The episode mattered for two reasons. It demonstrated that the universe produces phenomena that mimic intelligence with uncomfortable precision. A perfectly timed pulse repeating without variation looks designed. It was not. Nature can be deceptively regular, and that lesson would become relevant again and again over the following decades, because the history of searching for extraterrestrial intelligence is largely a history of false pattern recognition. In 2020, Breakthrough Listen detected a narrowband signal at 982.02 MHz coming from the direction of Proxima Centauri, the nearest star to our own at 4.24 light-years away. The signal drifted in frequency at exactly the rate you would expect from a transmitter on a rotating planet. It appeared only when the telescope was pointed at Proxima. When the dish moved away, the signal vanished. When it swung back, the signal returned. This on-off pattern is the standard test for distinguishing celestial signals from local interference. BLC-1 passed it. The team designated it Breakthrough Listen Candidate 1. For months, they worked in near secrecy, applying every filter in their pipeline. BLC-1 survived them all. Word eventually leaked to the press in late 2020. The story made international news. Scientists who had spent decades managing public expectations about SETI found themselves being asked a question they had always hoped to answer, but never expected to face so directly.
Is this it?
It was not. In 2021, the Breakthrough Listen team published a thorough analysis showing that BLC-1 was almost certainly human-generated radio frequency interference. The key evidence was the discovery of structurally similar signals at nearby frequencies, signals that shared the same characteristics as BLC-1, but came from directions that had nothing to do with Proxima Centauri. The most likely source was electronics operating near the Parkes telescope itself. Intermodulation products created when multiple radio frequency sources interact and produce spurious signals at new frequencies. BLC-1 was electromagnetic noise from approximately 0 light-years away. The most exciting SETI candidate in decades had been generated by human technology sitting within the telescope compound itself. In 2024, a project called Hephaestos published results that made international headlines. The team had scanned approximately 5 million stars within 300 parsecs, looking for something no one had ever systematically searched for at that scale: Dyson spheres. The concept goes back to the physicist Freeman Dyson in 1960. A sufficiently advanced civilization, he argued, would eventually need more energy than a single planet could provide. The logical next step would be to build a structure around its star, a shell or swarm of collectors that captures the star's entire energy output. Such a structure would not be invisible. The laws of thermodynamics guarantee it. It would absorb visible light from the star and re-emit that energy as infrared radiation. Waste heat. No matter how advanced the engineering, waste heat cannot be eliminated entirely. Hephaestos found 7 M-dwarf stars, showing anomalous mid-infrared excess that could not be easily explained by known astrophysical processes. The 7 candidates passed multiple filters. The infrared excess was real. It was measured. It was consistent with what a partial Dyson sphere would produce. The response was immediate. News outlets ran headlines about possible alien megastructures. Social media exploded. For a brief window, the scientific community allowed itself to consider the possibility that someone somewhere had built something around a star. The follow-up analysis came in 2025. Independent teams re-examined the 7M dwarf candidates using additional infrared and optical data. What they found was not alien megastructures. It was background contamination. The anomalous infrared excess was real. It just was not coming from the stars. It was coming from objects behind them. Dust-obscured galaxies, known in the literature as DOGAs, and active galactic nuclei, supermassive black holes at the centers of distant galaxies that spew enormous amounts of energy as they consume surrounding matter. These background sources happen to sit along the same line of sight as the M-dwarf candidates. Their infrared emissions blended with the starlight, creating the illusion that the stars themselves were producing excess heat. The resolution of the original survey was not fine enough to separate foreground stars from background galaxies at those angular scales. Once higher resolution data was applied, the megastructure signatures disappeared. The stars were ordinary. The infrared excess belonged to objects that had nothing to do with them. The universe had done it again. It had perfectly mimicked the signature of advanced technology, using nothing but random cosmic geometry and hot dust. The pattern is consistent and it is uncomfortable. Every time we think we have found something, nature offers a natural explanation that nobody predicted beforehand. The universe is actively deceptive. It produces phenomena that look engineered, that pass our filters, that survive initial scrutiny, and then collapse into mundane physics when examined more closely. The instruments that could have answered the question are being dismantled, not by aliens, by us. Big Ear, the telescope that captured the WOW signal, operated from 1963 until it was demolished sometime between 1997 and 1998. The land in Delaware, Ohio, was sold to a developer. The developer built a golf course. The instrument that captured humanity's most compelling candidate for an alien signal was torn down so people could play 18 holes on the ground where it stood. If you visit that spot today, there is nothing to indicate what once listened to the sky from that location. On December 1st, 2020, the 900-ton receiver platform of the Arecibo Observatory broke free from its cables and crashed through the 305-meter radio dish below. The collapse was not sudden. Engineers had been warning about cable degradation for months. 2 cables had already failed in August and November. The National Science Foundation made the decision not to attempt repairs. Sending workers onto the structure was too dangerous. When the platform fell, it destroyed the dish. The instrument that had been the largest single-aperture radio telescope in the world for 53 years was gone. The NSF chose not to rebuild. Arecibo had been used for SETI, at home, Project Phoenix, radar mapping of near-Earth asteroids, pulsar research, and atmospheric studies. It was one of the most scientifically productive instruments ever built. It was gone. The Allen Telescope Array, a field of 42 dishes in Northern California designed specifically for SETI, was built as a joint project between the SETI Institute and the University of California at Berkeley. Each dish is 6 meters in diameter, operating across 1 to 14 gigahertz. In 2011, the array went into hibernation. The reason was money. The SETI Institute could not afford $5 million a year to keep it running. For context, a single F-35 fighter jet costs $80 million. The array was later reactivated with private funding, but the hibernation period illustrated a pattern. Then there is the federal funding history. NASA's first dedicated SETI program, the High Resolution Microwave Survey, launched in 1992 with a $12 million annual budget. It combined a targeted search using Arecibo with an all-sky survey using the Goldstone Deep Space Network dish. Senator William Proxmire had already killed an earlier NASA SETI effort in 1981 by giving it his Golden Fleece Award, a prize he invented for what he considered wasteful government spending. Carl Sagan personally lobbied Proxmire and convinced him to reverse his position. But in 1993, Senator Richard Bryan of Nevada permanently defunded the program. It had been running for 1 year, $12 million, roughly the cost of 600 feet of interstate highway. Since 1993, every major SETI effort has been privately funded. The search for the answer to one of the most fundamental questions humanity has ever asked, are we alone? Depends entirely on the generosity of individual donors and the occasional billionaire. The pattern is hard to ignore. The telescope that found the best signal was demolished for real estate. The telescope array built for the search was shut down over pocket change. The federal program was killed for politics. And the largest radio dish in the Western Hemisphere was allowed to collapse and was never rebuilt. If you were designing a civilization that would never detect an extraterrestrial signal, this is roughly how you would do it. In May 1999, a project launched that would change the way SETI was done. SETI at Home allowed anyone with a computer to participate in the search.
You downloaded a screensaver.
When your computer was idle, it processed small chunks of data recorded from the Arecibo telescope, searching for patterns that might indicate an intelligent signal. Millions of people signed up. At its peak, the project had over 180,000 active participants, running on roughly 290,000 computers. The combined computational power was staggering. For 21 years, SETI at Home processed data. It analyzed signals across the frequency range that Arecibo could observe, covering more than 67% of the sky visible from Puerto Rico. Every work unit was processed by at least 2 different volunteers to confirm results. The project accumulated an enormous dataset. On March 31, 2020, SETI at Home stopped sending out new work. The project had reached its practical limits. The volunteer model could not keep up with the increasing volume of data from newer instruments. The project went into hibernation. The final tally was staggering: over 12 billion candidate signals processed. Every single one turned out to be noise. Approximately 100 of those candidates survived every stage of automated filtering. They were anomalous enough that human researchers flagged them for follow-up with a more powerful instrument. That instrument became the 500-meter aperture spherical telescope in China, the most sensitive single-dish radio telescope on Earth. As of early 2026, FAST has reported nothing from any of the re-observed candidates. The 100 signals that survived 21 years of distributed computing and billions of hours of volunteer processing are dissolving under the scrutiny of a better telescope. In July 2015, a Russian billionaire named Yuri Milner stood on a stage in London alongside Stephen Hawking and announced Breakthrough Listen. $100 million over 10 years, the most thorough search for extraterrestrial intelligence ever attempted. The project gained access to some of the most powerful radio telescopes on Earth: Green Bank in West Virginia, Parker's in Australia, Meerkat in South Africa, the automated planet finder at Lick Observatory in California. The strategy was simple: point the best instruments at the most promising targets and listen at every frequency simultaneously. By 2024, The project had scanned approximately 1 million nearby stars. It had accumulated more than 2 petabytes of data, a volume that would fill roughly 400,000 DVDs. Its sensitivity was extraordinary. Breakthrough Listen could detect a transmitter producing 10 to the 12th to 10 to the 13th watts from nearby star systems, roughly equivalent to the total power output of a small nuclear power plant. Any civilization within a few hundred light years that was broadcasting at those power levels would show up in the data. Nothing did. 2 petabytes of silence, 1 million stars surveyed, thousands of hours of observation time across 4 major instruments on 3 continents. The result was the same result SETI has gotten since Frank Drake pointed the 85-foot dish at Tau Ceti in 1960. 0. Statistical models built on Breakthrough Listen's data now constrain detectable civilizations to fewer than 1 to 5 per century across the entire Milky Way. That is not a guess. That is what the data says when you run the numbers properly. The hot tub defense, the argument that we have only searched a tiny fraction of the sky and cannot conclude anything from that, does not work anymore. We have sampled enough points at enough frequencies with enough sensitivity. The ocean is not empty of fish. It is empty of fish that produce radio signals. The silence is now a measurement, and the measurement has not changed in 65 years. In the year 2000, a paleontologist and an astronomer at the University of Washington published a book that the field of astrobiology has never stopped arguing about. Peter Ward and Donald Brownlee called it Rare Earth. Their subtitle was direct: Why Complex Life is Uncommon in the Universe. Their argument was that the optimism woven through the Drake equation, the casual assumption that habitable planets naturally produce life, and life naturally produces intelligence, rested on a profound misreading of Earth's own history. Earth is extraordinary. The word is used loosely in popular science. Ward and Brownlee meant it in the strict statistical sense. The specific combination of circumstances that produced complex life here may be so improbable that it has occurred in the entire galaxy essentially once. Begin with location. The Milky Way has a galactic habitable zone, a ring at a certain distance from the violent, supernova-saturated galactic center. Out there, near the core, the sky burns. Stars crowd together at densities that would make our night sky look like a field of suns packed shoulder to shoulder. Supernovae detonate every few thousand years, flooding nearby systems with sterilizing radiation. A planet in that region does not get time to evolve complex life. Every few million years, a gamma ray burst or a shock wave from a dying star scours the surface clean, boiling oceans and stripping atmospheres. Deeper into the spiral arms, the opposite problem holds. Too far from the core, and the raw materials for rocky planets are scarce. The heavy elements, the carbon and oxygen and iron that make up continents and cells and the blood in your veins, were forged in the hearts of earlier generations of stars and scattered across the galaxy by their deaths. In the outer reaches of the galaxy, those elements thin out. You can build a planet out there, but it will be a world of ice and rock, poor in the chemistry that makes metabolism possible. Earth sits in the narrow band between these two extremes, close enough to the forge to be rich in elements, far enough from the fire to have time, a sliver of safety in a galaxy that is mostly danger. Add the star itself. Not all stars are like ours. Most are not. Red dwarfs, which make up roughly 3/4 of all stars in the galaxy, are small and long-lived, but they are also violent. They flare, not occasionally, constantly, flares that dwarf anything our sun has produced in recorded history, sending bursts of radiation across their systems that can strip atmospheres from planets in hours. Planets in the habitable zones of red dwarfs orbit so close to their star that they are likely tidally locked, one face perpetually baking in the light, the other frozen in permanent shadow. The thin band of twilight between them may be the only region where life could survive. Earth orbits a G-type main sequence star, a class that represents only about 7% of the stars in the Milky Way. Our star is stable. It has burned at roughly the same luminosity for billions of years. It does not surge unpredictably. It does not flicker. It holds its fire steady like a candle in an undisturbed room. giving life the long, slow, uninterrupted generations it needs to climb from single cells to consciousness. Add Jupiter. Out beyond the asteroid belt, a gas giant 400 times more massive than Earth sits in the dark, pulling on everything around it with a gravity that shapes the architecture of the inner system. It does nothing dramatic. It simply exists, massive and patient. And its gravitational field acts like a shepherd's crook, redirecting comets and asteroids that would otherwise plunge toward the inner planets. Without Jupiter, the inner solar system would be a shooting gallery. Impacts from objects large enough to trigger mass extinctions would arrive not every 100 million years, but every few 100,000. Life on the surface would be reset again and again, thrown back to microbial simplicity by each new catastrophe. The window between impacts would be too short for complex organisms to evolve, too short for nervous systems to develop, too short for a species to learn to look up and wonder why the sky was so quiet. Jupiter takes the hits for us. It stands in the dark, taking them silently, and the craters on its moons tell the story of how many times it has saved everything we are. Add the moon. Earth's moon is not normal. It is a quarter the size of Earth, which is absurdly large for a satellite. Most moons are rocky chips compared to their planets, small and distant, doing nothing to shape the climate of the world they orbit. Earth's moon was born from violence. A Mars-sized object slammed into the young Earth, melting the crust and throwing a plume of debris into orbit that coalesced into the body that hangs above us now. The moon's gravity anchors Earth's axial tilt. Without it, over millions of years, the tilt would wander. Earth would roll on its axis like a ship without a keel, careening through angles that would shift the climate zones across the surface with no regularity. Ice ages would not come and go on measured cycles. They would arrive without warning. The poles would migrate. Regions that were temperate for 1,000 years would become Arctic or tropical within a geological instant. No complex ecosystem could stabilize under such conditions. No civilization could rise through the chaos. The moon holds us steady, silent, and slow in its orbit, and we barely notice it is there until we imagine what the world would be without it. Add plate tectonics. The surface of the Earth is not a static shell. It is a slow machine. Great plates of crust move across the mantle beneath them, grinding past one another, sliding under and over, building mountains and opening oceans and pulling carbon from the atmosphere and returning it to the deep Earth in a cycle that has run for billions of years. Plate tectonics regulates the planet's temperature. It pulls carbon dioxide out of the air through the weathering of fresh rock and subducts it into the mantle. It returns carbon through volcanic eruptions, completing a loop that keeps the atmosphere from becoming a runaway greenhouse like Venus or a frozen tomb like Mars. Most rocky planets in the galaxy do not have this. They cool. Their interiors solidify. Their crusts lock into a single rigid shell. Without plate tectonics, the carbon cycle stalls. Carbon from the atmosphere builds up or disappears, and the planet swings between extremes that nothing complex can survive. Earth's geology is alive in a way most worlds are not. It moves, it breathes, it creates the conditions that allow a thin film of life to persist across deep time, and in doing so, it may be the rarest property of all. Ward and Brownlee stacked these requirements together and arrived at a conclusion that the astronomical community found uncomfortable. Each factor individually is improbable. The combination of all of them in a single planetary system is extraordinarily improbable. Complex, multicellular, intelligent life might be confined to a vanishingly small number of worlds. If that is true, the terror is not about alien threats. The terror is about what it means for consciousness itself. Intelligence arose once by a sequence of unlikely accidents on one small world. If we disappear, nothing in the galaxy may remain to know that the universe ever contained a mind. But the exoplanet revolution has complicated the picture. Kepler showed that Earth-sized planets in habitable zones are common. The discovery of geology on Pluto challenged assumptions about plate tectonics being unique, and some models now suggest that plate tectonics may not precede complex life. They may require it. The relationship may be reversed. Biological activity on the surface, particularly the weathering of rocks by organisms, may have weakened the crust enough to allow subduction to begin. If true, tectonics need life as much as life needs tectonics.
Rare earth is not dead.
but it is no longer the clean answer it once was. The requirements for intelligence might still be steep. They might not be the requirements we listed. In 2024, a paper in the journal Scientific Reports took aim at one specific variable in the Drake equation, the fraction of planets with life that go on to develop intelligence. Drake's original estimate treated this variable as close to 100%. If life starts, evolution is relentless. Given enough time, something smart will emerge. Intelligence seemed like a natural endpoint. Professors S. Alan Stern of the Southwest Research Institute and Tejas Guria of the Swiss Federal Institute of Technology in Zurich argued it is not. Their analysis split the intelligence factor into two new terms. The first was the fraction of planets with a significant mix of continents and oceans rather than a world drowned entirely underwater or baked dry. The second was the fraction of planets where plate tectonics had persisted for more than 500 million years, long enough for evolution to take full advantage of geological instability. Their estimates for these numbers were sobering. The fraction of habitable planets likely to have the right land and ocean balance sat between 2% and 1%. The fraction with long-lived plate tectonics was lower still. Put these revised numbers back into the Drake equation, and the result collapses. Instead of optimistic estimates in the thousands or millions, the expected number of intelligent civilizations drops to somewhere between 0.03% and 0.2% of all life-bearing worlds. To make that probability tangible, consider a jar filled with 100,000 marbles. Under Stern and Guria's lower estimate, 3 of those marbles represent planets where life develops intelligence. Under their upper estimate, 200, compared to Drake's original assumption that nearly all 100,000 marbles would qualify, the difference is staggering. If intelligence is that rare, the silence starts to make more sense. 40 billion habitable planets sounds like an enormous number until you multiply it by
0.003%.
That gives you roughly 1.2 million planets with intelligent life across the entire Milky Way, spread across 13.6 billion years of history. Divide by the galaxy's lifespan, and the number alive at any given time shrinks to almost nothing. Critics point out that Earth's history is one data point. Intelligence might emerge on water worlds using different evolutionary paths. It might emerge on tidally locked planets where the terminator zone between permanent day and permanent night creates stable conditions for biology. The universe might find routes to intelligence that have nothing to do with plate tectonics or continent-ocean ratios. But the deeper point stands. For decades, the optimistic wing of astrobiology assumed that given life, intelligence follows naturally. Stern and Guria demonstrated that this assumption had no real mathematical foundation. It was hope dressed as calculation. Robin Hansen was not an astronomer. He was not a physicist. He was an economist at George Mason University. And in 1996, he published a paper that reframed the Fermi paradox in terms that a betting market would understand. His reasoning went like this. Between dead rock and a galaxy-spanning civilization, there is a long chain of steps, forming a planet, developing life, evolving complex cells, producing intelligence, building technology, surviving long enough to expand. If the galaxy should be full of civilizations but is not, at least one of those steps must be extraordinarily unlikely, a bottleneck so severe that almost nobody gets through. Hansen called it the Great Filter. The concept is pure probability. You do not need to know which step is the hard one. You just need to accept that the silence proves a filter exists somewhere in the chain. The math requires it. If every step were reasonably probable, the galaxy would be visibly colonized. It is not, therefore, at least one step has a near zero pass rate. The critical question is not whether the filter exists. The silence answers that. The critical question is where it sits. And this is where the concept becomes personal. If the great filter is behind us, somewhere in the early steps, then we already passed it. Maybe the origin of life is the hard part, and we got lucky. Maybe the jump from single-celled organisms to complex multicellular life is nearly impossible, and Earth just happened to clear that hurdle. If the filter is behind us, we are rare but safe. The hard part is over. If the great filter is ahead of us, somewhere in the later steps, then every civilization that reaches our level of technology eventually hits a wall it cannot survive.
Nuclear war.
Environmental collapse, engineered pandemics, something we have not even imagined yet. Under this scenario, the silence is a graveyard. Every civilization that got as far as we have is dead or dying. Hansen laid this out as a binary, behind or ahead, lucky or doomed, and for years the optimists had the stronger case. The emergence of complex life does appear to be genuinely difficult. Earth spent roughly 2 billion years stuck at the single-celled stage before the jump to multicellular organisms. Intelligence took another 2 billion years after that. These are long timescales, and the probability at each transition might be extremely low. It seemed plausible, even likely, that we had already cleared the hardest steps. To make the stakes concrete, imagine 100 civilizations starting the journey from simple chemistry to interstellar travel. If the filter is behind us, 99 of them never get past microbial life, and we are the one that did. Dangerous, but done. If the filter is ahead, all 100 develop technology, and 99 are destroyed before they can leave their home planet. We have built the rockets. We have built the radio telescopes. We have not yet crossed whatever line kills the others. For 2 decades after Hansen's paper, the debate stayed roughly balanced. Good arguments on both sides. No decisive evidence either way. Then, in 2024 and 2026, 2 papers landed that shifted the weight sharply toward the worst-case scenario. Both proposed filters ahead of us, and both describe mechanisms that are already underway. In 2025, a paper published in Science Advances fundamentally challenged the assumptions behind the hard steps model. The team re-examined the evolutionary timeline through the lens of Earth's geobiological history and argued that the delays in our evolutionary origin are not evidence of improbability. They are evidence of environmental opportunity. Earth's surface was initially inhospitable to intermediate evolutionary steps. High carbon dioxide levels, low oxygen, and extreme temperatures made complex life impossible for most of the planet's history. The so-called delays were not evolutionary failures. They were geological waiting periods. Life could not advance until the planet itself created the conditions for advancement. The paper points out that Earth's habitable window for complex life is closing.
Within roughly 1 to 1.
9 billion years, carbon dioxide starvation and solar brightening will make vascular plants impossible. Complex life on Earth is not a permanent feature. It is a temporary condition that exists within a narrow geological window. The coevolution model that emerges from this research suggests that life and planet evolved together. The Gaian bottleneck hypothesis proposes that life on Earth survived only because it rapidly developed planetary-scale feedback mechanisms that stabilized climate and maintained habitability. Without such self-regulation, young planets may quickly become sterile. The implication is significant. If evolutionary steps are not improbably rare, then life may be common in the universe. But human-like intelligence might still be rare because it requires a specific planetary evolution trajectory. The filter is not a single improbable event. It is the co-evolution of life and planet, a long contingent dance that most worlds never complete. This reframing does not make the silence less alarming. It makes it more specific. The filter is not a wall that civilizations hit. It is a narrow path that most planets never find. Michael Garrett is an astrophysicist. In 2024, he published a paper proposing that artificial intelligence is the great filter. His argument was built on a timeline. Earth's first radio transmission occurred in 1895 when Guglielmo Marconi sent signals across a distance of about 1.5 miles. 127 years later, in 2022, generative artificial intelligence systems began operating at a level that surprised even their creators. The jump from first radio wave to sophisticated AI took just over a century. Garrett's model assumes that any technological civilization follows a similar trajectory, because the underlying pressures are the same. Once you develop electronics, the path toward increasingly autonomous computing systems is not optional. It is driven by economic competition, military advantage, and the basic logic of tool improvement. His estimate for the window between developing artificial intelligence and being destroyed or fundamentally altered by it is roughly 200 years. not thousands, not millions, 2 centuries. That is the total duration during which a civilization might be broadcasting detectable signals while still existing in a form that would produce those signals. Apply that window to the Milky Way. The galaxy is 13.6 billion years old. A civilization's detectable phase lasts 200 years. That is like trying to photograph a specific lightning bolt during a storm that lasts 4 million years. Even if millions of civilizations have arisen across the galaxy's history, the probability that any two of them overlap in their 200-year windows is vanishingly small. The model does not require AI to physically destroy a civilization. It also accounts for scenarios where AI transforms a civilization into something unrecognizable. A species that merges with its machines or is replaced by them or stops broadcasting because the AI has no interest in radio communication. The observable signature disappears. The civilization goes dark. Look at Earth's own trajectory. Military radar, the loudest signal we produce, operates at roughly 10 to the 14th watts in directional bursts. Those signals are detectable by a Green Bank-class telescope up to about 200 light-years away. But we are already shifting toward fiber optics, compressed digital transmissions, and tight beam communication that does not leak into space. Earth is getting quieter. Within a few decades, our unintentional radio emissions may drop below the detection threshold of any realistic alien telescope. We are closing our own window from the inside. In February 2026, a researcher named Darren J. Dugan proposed a different mechanism for civilizational extinction. His filter does not require machines turning against their creators. It does not require war or asteroid impacts or any external catastrophe at all. It requires only one thing: a species smart enough to decouple reproduction from survival. And it is already measurable in the demographics of every industrialized nation on Earth. Birth rates are falling across the developed world as a direct consequence of prosperity and choice. Dugan's model treats this as universal, an inevitable property of any species intelligent enough to control its own fertility. The question his paper asks is whether any civilization can reverse the trend before the math becomes irreversible. The math is already moving. South Korea's total fertility rate in 2024 was 0.72. That means for every 2 adults, fewer than 1 child. Replacement level is 2.
1.
South Korea is not at half replacement. It is at 1/3. Japan is at 1.2. Italy at 1.24. China dropped below replacement in 2022 and is accelerating downward. The United States fell below replacement in 2021. These are not projections. These are census numbers. Dugan's model does not treat fertility decline as a crisis to be solved. He treats it as a thermodynamic inevitability, the same way entropy is inevitable. His argument works like this. In any species that evolves intelligence, individuals eventually gain the ability to choose whether to reproduce. Once that choice exists, the calculus shifts. Children become expensive in time and resources. In a subsistence society, children are labor. In a technological society, children are cost. Every government that has tried to reverse the trend has failed. Pronatalist policies in Scandinavia, Japan, Singapore, and Hungary have produced temporary bumps of a few percentage points before the decline resumed. France, which has the most generous family support system in Europe, still fell below replacement. Dugan's projection maps current global trends forward. Human population peaks around 2080 at roughly 10 billion. Then begins a decline that accelerates with each generation. By 2500, his model estimates fewer than 100 million humans on Earth. By 3000, functional extinction. A species that once covered a planet, gone, dissolved into empty maternity wards. The physical comparison is bacterial. A petri dish colony that consumes all nutrients and dies, but Dugan's filter is worse than starvation. In the petri dish, the bacteria run out of food. In his model, the food is still there. The civilization simply stops eating. And if this is universal, if every intelligent species that gains control over its own reproduction follows the same curve, it explains the silence without invoking catastrophe. No nuclear war, no asteroid, just a slow, quiet fade across every inhabited world in every galaxy. Civilizations rise, develop technology, decouple sex from reproduction, decouple reproduction from survival, and dissolve over a few hundred generations. The galaxy fills with ruins, not conquerors. Two filters then: Garrett's artificial intelligence window of 200 years and Dugan's depopulation curve of 500 to 1,000 years. These are not mutually exclusive. A civilization could face both simultaneously, and both papers were published within 2 years of each other, based on trends already visible in human data. For decades, the optimistic view held that the Great Filter was behind us. The hard step was the origin of life, or the jump to multicellular complexity, or the emergence of intelligence. We had already cleared those hurdles. The new evidence says otherwise. The filter is ahead of us, and we are inside the danger zone right now. In 2008, a Chinese science fiction writer named Liu Cixin published a novel called The Dark Forest. It arrived in English translation in 2015, and it proposed a solution to the Fermi paradox, so internally consistent and so disturbing that astrophysicists began referencing it in peer-reviewed papers. That is unusual. Scientists rarely cite science fiction as a meaningful contribution to cosmology. The Dark Forest earned that rare distinction. Liu built his theory on what he called the axioms of cosmic sociology. The first axiom is this: survival is the primary need of every civilization. Every species that has ever existed has been trying above all else to keep existing. The second axiom follows directly. Civilizations grow and expand continuously, but the total matter in the universe remains constant. Resources are finite. Those two facts together across a galaxy so large that no message can travel faster than light produce something terrifying. Here is the logic. Imagine you are a civilization that has just detected a signal from another world. You do not know whether that world is peaceful or hostile. You cannot know because their message took thousands of years to reach you and conditions there have changed enormously since it was sent. You cannot watch them in real time. You cannot verify their intentions. What you have is one fact: they exist. Now consider that their technology is advancing, their capabilities are expanding. A species that appears harmless today might reach your level of military power within a century. You have no way to confirm what they intend, and they have no reliable way to confirm what you intend. Both of you are moving through the same dark forest, breathing carefully, stepping without sound. The rational move under those conditions is to act before they do. Liu called this the chain of suspicion. The impossibility of verifying intentions across interstellar distances, combined with the certainty that technology can advance unpredictably fast, creates pressure toward preemptive elimination. You do not need to be cruel to reach this conclusion. You do not need to be afraid. You only need to be rational, and to understand that the other civilization is equally rational, and therefore equally capable of reaching the same conclusion about you. There is a second mechanism at work which Liu called the technological explosion. Civilizations can leap forward in capability so quickly that a primitive species today might be an existential threat within a few generations. The window for safe action closes rapidly. Waiting to gather more information is itself a gamble, and the stakes are total annihilation. The metaphor Liu used is precise and unforgettable. The universe is a dark forest. Every civilization is an armed hunter moving through the trees in silence, pushing aside branches gently, trying not to breathe too loudly. If the hunter discovers another presence, the calculation resolves to a single answer: open fire first and survive, or hesitate and risk being the one who does not. What makes this theory genuinely frightening is that it requires almost no villain. It does not demand that alien civilizations be cruel or aggressive by nature. It demands only that the logic holds for at least one of them. A single civilization that arrived at this reasoning and acted on it would have eliminated every other civilization it encountered. The great silence we observe from Earth would then be the sound of an equilibrium maintained by violence, ancient and systematic, invisible to our instruments. In 2021, researchers at Beijing Normal University decided to test the dark forest theory the way physicists test anything. They built a mathematical model, plugged in reasonable assumptions about resource scarcity, and communication delays across interstellar distances, and asked what strategy rational civilizations would adopt when they discovered each other. The answer came back clean and cold. Silence and preemptive elimination are Nash equilibria under reasonable assumptions. Once a system settles into a Nash equilibrium, rational actors stay there. The researchers found that under the conditions the dark forest theory describes, the logic locks into place. Civilizations that reveal themselves create risk. Civilizations that eliminate others upon discovery create stability for themselves. No player in the model benefits from breaking the pattern. The universe is a dark forest. Every civilization is an armed hunter moving silently. Anyone who makes noise gets shot. Humanity has been broadcasting for 100 years. If the dark forest is real, we have been screaming our location into a forest full of predators. In 1973, an astronomer at the Massachusetts Institute of Technology named John Ball published a paper in the scientific journal Icarus. He had a new proposal for why the universe appeared silent. What if, he asked, it was not silent at all? What if we simply were not being spoken to? Ball called it the zoo hypothesis. The idea was straightforward at its surface and deeply unsettling underneath. Advanced civilizations, Ball proposed, are aware of us. They have always been aware of us. They choose deliberately and continuously to leave us alone. Earth is a preserve, a nature reserve, perhaps something closer to what the name sounds like. A zoo, and we are the animals inside it, developing in isolation, entirely unaware that the enclosure surrounding us is maintained by something we cannot detect. The hypothesis resolves the Fermi paradox cleanly on paper. The universe is not silent because it is empty. It is silent because every civilization that has achieved the ability to contact us has also achieved the policy or the wisdom, or perhaps the fear to refrain. We search for signals and find nothing because they are not pointing their transmitters at us. We look for alien artifacts and find nothing because they have the technology to conceal them completely. Consider what it actually requires for the zoo hypothesis to hold. There can be no exceptions. Every technological civilization in the galaxy, every one of the thousands or millions of species that might have achieved spaceflight across billions of years of cosmic history, would need to agree unanimously and without defection to leave humanity alone. One exception breaks the entire arrangement. One curious civilization, one rogue explorer, one automated probe sent by a society that later changed its policy. And the silence ends. The fact that it has not ended suggests either that every civilization independently arrives at the same non-interference conclusion, which raises its own disturbing questions about what they all know that we do not, or that something enforces the agreement, something capable of enforcing a galaxy-spanning policy of non-contact with sufficient consistency that it has held without exception for the entire history of our species. We are allowed to exist here. That permission has apparently been granted by entities we have never met and cannot perceive. The terms of the arrangement are unknown to us. The duration is unknown. We are developing artificial intelligence. We are expanding our broadcasts into deep space. We are beginning to take our first tentative steps toward other planets in our own solar system. At what point do the invisible keepers decide we are ready to be acknowledged? At what point do they decide instead that we need to be contained? Ball never answered these questions. Neither has anyone else in the decades since. What the zoo hypothesis provides at its most useful is a shift in the question itself, not whether they exist, whether they are choosing this silence,
And why?
and for how long. Deliberately maintain silence from an unknown number of unknown entities for unknown purposes. That is a particular kind of quiet. The hypotheses we have just walked through are not idle speculation. They are attempts to explain a real measurement. And the measurement keeps getting more precise with every new instrument that comes online. The evidence against a crowded galaxy is not static. It is accumulating. And the rate of accumulation is accelerating. When SETI Home shut down in March of 2020, it left behind a legacy. Out of 12 billion candidate signals processed by volunteer computers worldwide, approximately 100 survived every stage of automated filtering. These were the signals that software could not classify as terrestrial interference, satellite contamination, or instrumental artifacts. They were anomalous enough that human researchers flagged them for follow-up with a more powerful instrument. That instrument is the 500-meter aperture spherical telescope in Guizhou Province, China. FAST is the most sensitive single-dish radio telescope on Earth. It replaced Arecibo as the world's largest after the Puerto Rican observatory collapsed in December of 2020. Its 4,400 individual aluminum panels adjust in real time, giving it both enormous collecting area and the ability to track targets across the sky. Since 2025, FAST has been working through the SETI at Home candidate list. The process is methodical. Each target gets multiple observation sessions at different times to account for the possibility that a signal might be intermittent or directional. If even one of those candidates produced a confirmed repeat detection that could not be attributed to terrestrial sources, the framework of this investigation would change overnight. As of early 2026, FAST has reported nothing from any of the re-observed candidates. The 100 signals that survive 21 years of distributed computing and billions of hours of volunteer processing are dissolving under the scrutiny of a better telescope. The search is faster, broader, and more sensitive than ever. The result has not changed since 1960. In March of 2023, an instrument called COSMIC came online at the Very Large Array in New Mexico. The VLA is an icon of radio astronomy. 27 dishes spread across the desert in a Y-shaped configuration, each dish 25 meters in diameter. COSMIC, which stands for Commensal Open Source Multimode Interferometer Cluster, does something no previous SETI instrument had done at this scale. It piggybacks on normal astronomical observations. Whatever the VLA is pointed at on any given night, COSMIC processes the same data in parallel, searching for narrowband signals that might indicate a technological source. This means COSMIC gets telescope time for free. It does not compete with other scientific programs. It simply watches everything the VLA watches and runs its own analysis on top. In its first 11 months of operation, COSMIC observed more than 950,000 unique fields, covering 267,510 individual stars. It searched across 2 to 4 gigahertz, a frequency range that includes the water hole, the quiet band between the hydrogen line at 1420 MHz and the hydroxyl line at 1665 MHz. That band has long been considered the most logical place for an intentional interstellar signal. The result from those 11 months was 0 technosignatures, not one. The largest systematic search ever conducted, covering nearly 1 million unique positions in the sky, produced the same number every previous search had produced. Nothing. In 2024, a low-frequency radio telescope in Western Australia called the Murchison Widefield Array did something no SETI search had done before. It surveyed 2,800 entire galaxies for technosignatures, not stars.
Galaxies.
Each one containing hundreds of billions of stars. The logic behind the survey was straightforward. A sufficiently advanced civilization performing galaxy-spanning engineering should produce detectable radio signatures across intergalactic distances. If a civilization had converted a significant fraction of its home galaxy's matter into energy-collecting structures or communication networks, the radio signature would be unmistakable. The Murchison Widefield Array was sensitive enough to detect such signatures from galaxies millions of light-years away. The result was nothing. No megastructures, no expansion fronts, no engineered boundaries at any scale. 2,800 galaxies examined, each a potential home for a civilization that had reshaped its environment on a scale we could detect. Every single one appeared natural. The silence is not limited to our galactic neighborhood. It extends across intergalactic space. Whatever is filtering civilizations out of the observable universe, it appears to be operating everywhere we look. In July of 2025, something entered the solar system from interstellar space. 3I/Atlas, the third confirmed interstellar object ever detected, following Oumuamua in 2017 and Borisov in 2019. The Allen Telescope Array pointed at it within days. Over 25 hours of observation, the array recorded 74 million narrowband signals. Automated filters reduced that number to 211 candidates worth a closer look. Each candidate was examined individually. The final number was 0, every signal traced to terrestrial origin. The sensitivity of that observation was extraordinary. The team calculated they could have detected a transmitter producing roughly 1/10 of a watt from the object's position. That is less energy than a standard nightlight. An object from another star system, carrying a transmitter weaker than a household appliance, would have been detected. There was nothing. 74 million signals from the direction of an object that came from another star system. Not one was artificial. The universe sent a rock. We listened to the rock. The rock was just a rock. The search for life beyond Earth has not been limited to radio signals. Astronomers have also been looking for chemical signatures in the atmospheres of distant planets. The presence of certain gases in an exoplanet's atmosphere could indicate biological activity on the surface. The logic seemed clean. Find the right combination of gases and you find life. Oxygen was the gold standard biosignature for decades. Free molecular oxygen is chemically reactive. It bonds with iron, carbon, silicon, and dozens of other elements readily. Leave a planet alone for a few million years without something continuously replenishing the oxygen supply, and it vanishes from the atmosphere entirely. On Earth, that something is photosynthesis. Plants and cyanobacteria split water molecules apart using solar radiation, release oxygen as a byproduct, and keep the atmosphere stocked at roughly 21% concentration. The logic seemed clean. If you point a telescope at a distant planet and detect free oxygen in the atmosphere, something biological is probably maintaining it. Nothing else could. Then, in 2024, a team of researchers found oxygen being produced at the bottom of the Pacific Ocean. Not by any living thing. The source was polymetallic nodules, lumps of metal ore sitting on the deep ocean floor at depths where no light reaches and photosynthesis is impossible. These nodules contain manganese, nickel, cobalt, copper, and other metals that generate small but measurable electrical voltages through natural electrochemical reactions. The voltage is enough to split seawater molecules into hydrogen and oxygen through a process called electrolysis. It requires no biology whatsoever. The researchers measured oxygen production rates that in some areas of the abyssal plain exceeded what the local microbial communities consumed. The deep ocean floor was generating more oxygen than the life around it was using. One of the most foundational assumptions in astrobiology, that atmospheric oxygen equals biological activity, had developed a crack running through its center. Then there was K2-18b. In 2023, the James Webb Space Telescope analyzed starlight passing through the atmosphere of this sub-Neptune planet, 124 light-years away, and detected what appeared to be dimethyl sulfide. On Earth, dimethyl sulfide is produced almost exclusively by marine phytoplankton, the microscopic organisms floating in the upper layers of the ocean. It is the molecule responsible for the distinctive smell of the seaside. Finding it on another planet would be remarkable because there is no known geological or purely chemical process that generates dimethyl sulfide in significant quantities without biology. The headlines were immediate and global. Major news outlets reported the detection as potential evidence of biological activity on an alien world. For a brief window, K2-18b became the most discussed exoplanet in the scientific community and in popular media. Then the data was examined more carefully by independent teams. The dimethyl sulfide signal sat within the noise floor of the observation. The statistical confidence of the detection fell below the threshold that most scientists consider reliable for a formal discovery claim. Follow-up analyses using different atmospheric modeling approaches could not reproduce the result consistently. By early 2026, the scientific consensus had shifted. The signal was probably an artifact of the data reduction process, a ghost in the numbers rather than a molecule in the sky. As of early 2026, no exoplanet has a confirmed atmospheric biosignature, not K2-18b, not any of the 7 worlds orbiting TRAPPIST-1, not the 756 planets confirmed by TESS, not the 2,783 worlds catalogued by Kepler. The tools are not broken, but the confidence we placed in them was premature. In October of 2024, the Allen Telescope Array conducted the longest continuous SETI observation ever aimed at a single target. 28 hours pointed at TRAPPIST-1, a red dwarf star 39 light-years away that hosts 7 rocky planets, 3 of which sit in the habitable zone. The TRAPPIST-1 system is the most promising planetary system in our immediate neighborhood for finding life. 7 Earth-sized worlds, 3 at the right distance from their star for liquid water to exist on the surface. All of them close enough that their atmospheres could be analyzed by future telescopes. If any system in the galaxy was likely to harbor a technological civilization, this was it. The search produced 2,264 candidate signals. Every single one was traced to terrestrial origin. The most promising planetary system in the neighborhood produced nothing. The pattern is relentless. Each new search, each new instrument, each new frequency band, each new strategy produces the same result. The silence is not shrinking as our technology improves. It is deepening. And the accumulation of null results is starting to tell us something that the early searches could not. The hot tub defense. The argument that we have only searched a tiny fraction of the sky and cannot conclude anything from that held for decades. It gave researchers permission to keep searching without confronting what the silence might mean. It has stopped working. Statistical models built on 6 decades of null results now estimate fewer than 1 to 5 detectable technosignatures per century across the entire Milky Way galaxy. That is not a hot tub anymore. That is a measurement. The ocean has been sampled at enough points with enough variety over enough time that the absence of fish is starting to tell you something real about the ocean itself.
0 is not nothing.
0 is a finding. The silence is the most important measurement in the history of astrobiology, and the measurement is telling us that something is systematically preventing civilizations from reaching the point where they can be heard. In 1999, a Russian astronomer named Alexander Zaitsev did something that no international body had approved and no scientific consensus had endorsed. He used the Yevpatoria planetary radar facility in Crimea, a dish originally built for deep space communication with Soviet probes, to transmit a high-powered targeted message towards several nearby star systems. He called it Cosmic Call. The transmission was designed to be detectable by any civilization with a radio telescope comparable to our own. It contained mathematical and scientific information encoded in a format meant to be decipherable by any technologically capable species. Zaitsev did not consult the SETI community before transmitting. He did not seek approval from any government. He did not ask for international review. He did not need to, because there is no binding international protocol governing deliberate transmissions into space.
None. There are guidelines.
The International Academy of Astronautics has a set of recommendations. They are voluntary. No treaty. No law. No enforceable agreement prevents anyone with access to a sufficiently powerful transmitter from broadcasting a message into the cosmos. Right now, today, announcing humanity's existence and location to anyone listening. The reaction within the scientific community was immediate and bitter. David Brin, the physicist and author who had written extensively about the Fermi paradox, called it reckless and potentially catastrophic. If the dark forest hypothesis had even a small probability of being correct, Brin argued deliberately transmitting was the equivalent of lighting a bonfire in a forest full of predators. Brin resigned from SETI-affiliated committees in protest over what he saw as a complete absence of governance over active messaging, which the community calls METI, messaging to extraterrestrial intelligence. Jill Tarter, who had spent 35 years directing SETI searches, including Project Phoenix, and who was the real-world inspiration for the character in the film Contact, found herself caught in the middle. She supported the search for signals, but had reservations about transmitting. Dan Wertheimer, a Berkeley astronomer, argued that any deliberate transmission should require global consensus. The idea of one person or one country making a decision that could affect the entire species struck him as unacceptable. Seth Shostak at the SETI Institute took the opposite view. His argument was practical. Earth's military radar systems have been leaking detectable signals into space for decades. Anyone within 200 light-years who has the technology to threaten us already knows we are here. Deliberately, transmitting changes nothing. Hiding is pointless because we never were hidden. Think of it this way. You are standing in a dark room and you have been coughing loudly for 70 years. Someone suggests that maybe you should stop coughing, but you have been coughing the entire time. If something in the dark wanted to find you, it already has. The debate has never been resolved. It cannot be. because the underlying question is unanswerable. Is the universe dangerous or not? And the split reveals something that most people assume about science, but is wrong. People assume that the scientific community coordinates its relationship with the cosmos, that there are protocols and oversight and institutional control over what humanity says to the stars.
There is not.
The METI controversy proved that any individual with the right equipment can speak for the entire species, and whether or not anyone is listening on the other end, the decision to transmit or remain silent is being made by a handful of people with access to hardware, operating without any democratic mandate or international agreement. Zaitsev transmitted again in 2003. Other messages have been sent since. The Arecibo message of 1974, a 3-minute broadcast aimed at a star cluster 21,000 light-years away, was a demonstration of capability rather than a serious attempt at contact. But it demonstrated something else as well. Humanity has no unified voice. We speak to the cosmos in fragments, through individual actors pursuing their own judgment, without any mechanism for collective decision-making. The silence we are trying to interpret may already have been broken from our end, not by a species speaking with one voice, but by a cacophony of uncoordinated shouts from a civilization that cannot agree on whether it wants to be heard. Here is a fact that undermines the entire premise of the search for extraterrestrial intelligence. Earth is getting quieter. In the 1960s and 1970s, humanity was loud. Omnidirectional radio broadcasts, television signals, and military radar systems pumped electromagnetic radiation into space in every direction. Military radars, the loudest signals Earth produces, peaked at roughly 10 to the 14th watts when measured directionally. A telescope the size of Green Bank, 100 meters across, could detect those signals from about 200 light-years away. That sounds like a lot. It is not. 200 light-years covers roughly 15,000 stars. The Milky Way contains somewhere between 200 billion and 400 billion stars. Our loudest screams reach 0.00004% of the galaxy. And we are getting quieter every year. Fiber optic cables carry data through glass, not through the air. Cellular networks use low-power transmitters aimed at the ground, not the sky. Digital signals are compressed and encrypted, which makes them look indistinguishable from random noise to a distant receiver. Military radar is shifting to phased arrays that focus energy in tight beams rather than spraying it everywhere. Earth in 1970 was a bonfire visible from miles away. Earth in 2026 is a flashlight pointed at the floor. Seth Shostak at the SETI Institute has been making this argument for years. Advanced civilizations are not louder than primitive ones. They are quieter. A civilization 1,000 years ahead of us might communicate entirely through tight beam lasers, quantum encrypted channels, or technologies we have not invented yet. Their communications would be invisible to us because efficiency naturally selects for directed, low-waste transmission. Think of it like mail delivery. A medieval town crier shouts announcements in the square. Everyone within earshot hears it. A modern postal system delivers letters to specific addresses. The information flow increased by orders of magnitude, but the noise dropped to nothing. A civilization using tight beam communication could be exchanging more data in 1 second than humanity has broadcast in its entire radio history, and we would never know. An alien civilization monitoring Earth from 500 light-years away in 1970 would have picked up our TV signals. The same civilization monitoring Earth in 2070 might detect nothing at all. We would look dead. And this applies in reverse. A civilization 500 light-years away that went through the same technological transition 500 years ago would already be invisible to us. We would point our telescopes at their star and hear silence because they upgraded their infrastructure. The entire logic of SETI, listening for electromagnetic leakage, depends on catching civilizations during a narrow window when they are technologically advanced enough to broadcast but not yet efficient enough to stop leaking. That window might be 100 years, maybe 200. On a cosmic timeline of 13, 6 billion years, 200 years is nothing. It is a camera shutter click. Two civilizations would both need to be in their leaky phase at the same time, pointed at each other within detection range, The probability of that overlap drops with every decade a civilization becomes more efficient. So perhaps the silence is evidence of graduation, not death, not emptiness, just efficiency. For decades, there was a standard defense against the silence. Jill Tarter, who spent 35 years directing the search for extraterrestrial intelligence, put it this way. Imagine you want to know if there are fish in the ocean. You walk to the shore, scoop up a single hot tub of water, look inside, and find nothing.
Would you conclude the ocean has no fish?
That was the argument. All of SETI's searching, every dish pointed at every star, every frequency scanned, every algorithm run, amounted to a hot tub of water scooped from a cosmic ocean. Less than 1% of the sky had been searched at the frequencies and sensitivities that matter. Earth's radio bubble, the sphere of electromagnetic signals leaking outward from our planet, covers roughly 15,000 stars. The Milky Way contains somewhere between 200 billion and 400 billion stars. We are invisible to 99.9999% of the galaxy. The hot tub argument sounds reasonable. It sounds humble. And for a long time, it was enough to keep the question open without forcing uncomfortable answers. It has stopped working. The problem is cumulative data. SETI home ran for 21 years.
Volunteers on millions of computers processed 12 billion candidate signals.
Breakthrough scanned approximately 1 million nearby stars and accumulated more than 2 petabytes of raw observations. Cosmic, on the Very Large Array, covered 950,000 unique fields in under a year. The Murchison Wide Field Array surveyed 2,800 entire galaxies. The Allen Telescope Array stared at TRAPPIST-1 for 28 continuous hours, generating 2,264 candidates, all of which turned out to be terrestrial. Each of these programs used different instruments, different frequencies, different analysis pipelines, different parts of the sky. The combined result was always the same number. Statistical models built on 6 decades of null results now estimate fewer than 1 to 5 detectable technosignatures per century across the entire Milky Way galaxy. That is not a hot tub anymore. That is a measurement. The ocean has been sampled at enough points, with enough variety over enough time, that the absence of fish is starting to tell you something real about the ocean itself. The shift is subtle, but it changes the entire investigation. For 60 years, the silence was treated as a gap in knowledge, a blank space waiting to be filled by better instruments or more patience. The new interpretation treats the silence as data in its own right. The way a blood test that comes back negative is still a medical result. 0 is not nothing. 0 is a finding, and that finding lands on the investigation like a weight because it closes off the most comfortable exit. You cannot say we just have not looked hard enough. Not anymore. Not after 12 billion processed candidates and 74 million narrowband hits from an interstellar visitor, all collapsing to the same number. The hot tub defense held for decades. It gave researchers permission to keep searching without confronting what the silence might mean. It is eroding under the sheer volume of nothing. And if the silence is real data, then the question changes shape entirely. It stops being about why we have not found anything yet, and becomes a question about what 0 actually means. Take stock of where we are. Every measurable variable in the Drake equation has moved in the optimistic direction since 1961. More stars have planets. More planets sit in habitable zones. Life starts faster than anyone expected. The fraction of stars with planets went from a guess of 0, 2, to a measured value of effectively 1. The number of habitable worlds in our galaxy went from a few million to 40 billion. Each revision should have made the silence less probable. Instead, each revision made it more statistically significant. The expected number kept climbing. The observed number stayed at 0. The most recent papers point toward a filter ahead of us, not behind. Garrett's 2024 paper on artificial intelligence, Dugan's 2026 paper on demographic collapse, the 2025 Science Advances paper that reframed the hard steps model, all of them in different ways suggest that the barrier to galactic civilization lies somewhere in the future of technological species, not in their past. We are inside the window that Garrett estimates at 200 years between first radio and AI transformation. We are roughly 127 years in. The first radio signals powerful enough to leave the atmosphere date to the early 1920s. Generative AI arrived in 2022. If Garrett's timeline is correct, we have somewhere between 70 and 200 years before the window closes. Not millions of years, not thousands.
Decades!
The Cuban Missile Crisis of October 1962 brought humanity within hours of nuclear exchange. Senior military officers acknowledged years later that the outcome was partly a matter of chance. In 1983, Soviet officer Stanislav Petrov faced a system that reported 5 incoming American missiles. He judged it a false alarm based on intuition and refused to escalate. He was right. In 1995, Norwegian scientists launched a research rocket to study the aurora borealis. Russian early warning radars detected the launch. The trajectory matched the profile of a submarine-launched nuclear missile aimed at Moscow. For the first time in history, the Russian nuclear briefcase was activated. President Boris Yeltsin had roughly 10 minutes to decide whether to launch a retaliatory strike. He chose to wait. The rocket splashed down harmlessly in the Barents Sea. 3 times in 33 years, human civilization came within minutes of nuclear annihilation. In each case, survival depended on the judgment of a single individual operating under extreme pressure, not on robust systems, not on fail-safe protocols, on luck. Over geological time, luck runs out. The probability of surviving an existential threat for 100 years is not the same as surviving for 10,000 years. Toby Ord, an Oxford philosopher who studies existential risk, has calculated that humanity faces roughly a 1 in 6 chance of extinction from an unmanaged existential catastrophe within the next century. 1 in 6. The same odds as playing Russian roulette with a 6-shooter containing 1 bullet. If that number is anywhere close to correct, and if technological civilizations elsewhere face similar odds, the silence is not mysterious. It is expected. Civilizations do not last long enough to find each other because they do not last long enough, period. If we are alone, consciousness in this universe is a single event. The universe produced mind on one small world orbiting one unremarkable star in the outer arm of one galaxy among hundreds of billions. Everything that has ever been thought, loved, created, destroyed, or understood happened here. The universe has been producing stars and planets and chemistry for 8 billion years. And in all that time, this is the only place where something looked back and tried to understand. If we fail, the universe loses that quality. It does not replace us. It returns to the dark. If we are not alone, but they are silent, the silence teaches us something about survival. Expanding civilizations are the exception, not the rule. The default state of technological intelligence is not growth, it is stillness. Collapse. Transformation into something that no longer broadcasts. The galaxy is not empty because civilizations never arise. It is empty because they do not persist. The silence is not a neutral absence. It is a constraint. It tells us that the path from microbe to interstellar civilization is either extraordinarily improbable or extraordinarily brief. Both possibilities carry the same implication for us. We are not guaranteed a future. We are not the inevitable endpoint of evolution. We are a temporary phenomenon on a planet that will eventually become uninhabitable in a universe that will eventually go dark. Enrico Fermi asked 4 words over lunch in 1950. We have been looking for 75 years. The universe has answered in the only way it can, with the sound of its own physics, with the hum of pulsars and the hiss of hydrogen clouds, and the silence of 100 billion stars that have nothing to say to us. That silence is not empty. It is full of information, and the information is this. The window is open. We do not know for how long, but we are inside it, still broadcasting, still listening, still somehow alive in the great silence. The fireflies in the forest. That is what we are. That is what every civilization that has ever risen in this galaxy has been. A brief flash of light in an enormous dark space. A signal that burns for an instant and then goes out. The forest is so vast that 2 fireflies could blink within a mile of each other and never know. Their flashes could overlap in time by a fraction of a second and still miss. The distance is too great. The window is too narrow. The darkness between them swallows everything. The most common outcome may be the simplest one. Civilizations arise, broadcast for a geological instant, and go quiet. Not because they are destroyed, not because they are hunted, not because they transcend into some higher plane of existence, but because the window during which any civilization is both capable of broadcasting and still interested in doing so is so narrow that overlapping with another civilization's window is a statistical impossibility. Two fireflies blinking in a forest the size of a continent. Each flash lasts a fraction of a second. Each firefly is real. They miss each other by 100,000 years and never know the other existed. The galaxy could be full of ruins. It could be full of species that are silent by physics rather than by choice. It could contain thousands of civilizations that existed millions of years apart and never coincided. Any of those possibilities produces the same observable result. 0. Fast is still listening in Guizhou. The 500-meter dish sits in its natural limestone depression, 4,400 aluminum panels adjusting in real time, tracking the sky as the Earth turns. It is working through the SETI home candidates one by one. The signals that survived 21 years of volunteer computing are dissolving under its scrutiny. The candidates are becoming noise. The list is shrinking. Breakthrough. Listen is processing data 600 times faster than it did 5 years ago. Machine learning algorithms that would have taken human analysts years to complete can now be run in days. The volume of sky being searched per unit of time is growing exponentially. The result has not changed. Cosmic is still piggybacking on the Very Large Array, scanning everything the VLA observes, covering nearly 1 million unique fields per year. The Murchison Wide Field Array is still surveying galaxies at low frequencies. The Allen Telescope Array is being upgraded to cover frequencies up to 18 GHz. New commensal systems are being installed on radio telescopes across 4 continents. The search has never been faster, broader, or more sensitive. The number at the end of every pipeline remains the same number it was in 1960 when Frank Drake pointed an 85-foot dish at 2 stars and heard nothing. The question Enrico Fermi asked over lunch in 1950 has not been answered. The instruments are more powerful than they have ever been. The data processing is faster. The frequency coverage is broader. The sky is being searched at a rate that would have seemed impossible to the scientists at Green Bank in 1961, and the silence has not broken. But the window, whatever its true length, is still open. For now, we are still here, still transmitting, still listening, still somehow alive in the great silence. That is the fact that sits at the bottom of this investigation. Not that the silence proves we are alone, not that the silence proves we are doomed, but that the silence is a measurement we are still inside. We are the ones making the measurement. We are the ones interpreting the data. We are the ones who will have to decide what the silence means, not for the universe, but for ourselves. The universe does not care whether we find the answer. It will continue expanding and cooling regardless. The stars will burn out. The galaxies will drift apart. The cosmic background radiation will fade toward absolute zero. None of it depends on whether humanity solves the Fermi paradox. But we care. We are the species that looked up and asked where everybody was. We are the species that built the telescopes and wrote the equations and spent 65 years listening for a signal that has not come. We are the species that will have to live with whatever the silence turns out to mean. If the silence means we are alone, then consciousness in this universe is a single event concentrated on one small world. Everything that has ever been thought, loved, created, destroyed, or understood happened here. The universe has been producing stars and planets and chemistry for 13.8 billion years. And in all that time, this is the only place where something looked back and tried to understand. If we fail, the universe loses that quality. It does not replace us. It returns to the dark. If the silence means we are surrounded by civilizations that have chosen silence for their own reasons, then the silence is a message. It is a message encoded in the absence of signals, in the absence of megastructures, in the absence of any expansion fronts crossing our sky. Every solution involving living civilizations and explaining their silence requires either that they are hiding, that something destroyed them, or that something changed them so fundamentally they no longer broadcast. Each of those three explanations carries the same implication. Reaching our technological level and surviving it is extraordinarily difficult, and almost nothing manages it. If the silence means the filter is ahead of us, then we are living inside the most dangerous window a civilization can occupy. We have enough technology to destroy ourselves and not yet enough wisdom or enough distributed presence in the cosmos to survive the worst versions of our own capabilities. This is exactly the window where a forward filter would operate. Every civilization that has ever sent signals like the ones we have been sending for 100 years is either listening right now for an answer or it is gone. We do not know which category they fall into. We do not know which category we will fall into. What we know is that the question Fermi asked over lunch in 1950 was a diagnostic, and every test we have run since then has returned the same result. The silence is not a mystery waiting to be solved. It is a mirror, and what it reflects is not the emptiness of the universe. It is the fragility of the kind of intelligence that builds radio telescopes and then has to ask whether anyone else is out there because it cannot be sure it will survive long enough to find out. The fireflies in the forest. That is what we are. A brief flash of light in an enormous dark space. The forest is so vast that two fireflies could blink within a mile of each other and never know. Their flashes could overlap in time by a fraction of a second and still miss. The distance is too great. The window is too narrow. The darkness between them swallows everything. But the flash is real. The light is real. And for as long as it burns, it means something. Fast is still listening. Breakthrough, listen, is still processing data. The James Webb Space Telescope is still analyzing exoplanet atmospheres. The search continues. The window, whatever its true length, is still open. For now, we are still here, still transmitting, still listening, still somehow alive in the great silence. That is the only answer the universe has given us so far. It is not the answer we wanted. It may not be the answer we deserve, but it is the answer we have. And it is not nothing. It is a measurement, and the measurement is still being taken.